So, we continue our discussion on the path integral approach to quantum mechanics, and on this opening slide we have Niels Bohr at the center. So, he was not the originator in the sense that Schrödinger or Heisenberg was, but then he was like the music director and the composer, and he explained quantum theory to everybody, including those who created it, including those who opposed it even after creating it, and it was due to Bohr that we learned so much about, we got so much insight in quantum mechanics. So now we are thinking about these alternative paths for a system to go from an initial point xi at an initial time ti to a final destination point xf at a time tf, all right. And we know from the conventional quantum mechanics, okay, which is the Schrödinger-Heisenberg quantum mechanics. That is what I will call as conventional quantum mechanics. We know that this probability amplitude is given by the time evolution operator, which is e to the minus I h t over h cross, right. So, we know this solution. This is conventional quantum mechanics. This is the time evolution operator which I have plugged in, and we are familiar with this. We have discussed it in our previous classes, okay. And that this is coming from the Schrödinger solution to the Schrödinger equation. We discussed different possibilities that the Hamiltonian at a later time may commute with the Hamiltonian at time t1, or it may not, and depending on that you have different kinds of solutions. If the Hamiltonian at different times do not commute, you have got the Dyson series. So all of these things we have discussed in conventional quantum mechanics, okay. We have also learned that in conventional quantum mechanics, when you use energy eigenkets, which are eigenkets of an operator which commutes with the Hamiltonian, then you get stationary state solutions, and these stationary states, we discussed the term stationary, and in our previous classes we spent some time discussing it. We also discussed why it is called as a stationary state, and these states are stationary does not mean that they are static. They are not static, they do change with time, and the manner in which they change with time is given by this oscillatory phase, e to the minus I omega t, or e to the minus I e over h cross t, right. This is the phase which is a sum of cosine and sine functions, right, and it is this phase which changes with time, okay. The phase angle is this omega t, okay. It changes, it is a time dependent phase. This describes the dynamical evolution of the system, and this is what is called as the dynamical phase. So, this is the dynamical phase, and this is how the pure eigenstates of an operator which commutes with the Hamiltonian evolve with time. So, there is this time dependence, and with this time dependence you can predict what the state vector will be at a later time, because it is going to be the same, its modulus is going to be the same, only the phase will change according to this particular prescription, okay. So, now we insert a unit operator, we resolve this unit operator in momentum eigenstates, okay. That is what we have done here in this step, you can see it, right. Now, the Hamiltonian can be seen to be acting on its right, where you have got the position eigenstates, or on its left where you have the momentum eigenstates. But the Hamiltonian itself is the sum of the kinetic energy operator, which is made up of the momentum operators and also the potential energy operator, which has got the position operators, and they do not have simultaneous eigenstates, right? The position and the momentum operators are not simultaneously diagonalizable. They do not have simultaneous eigenstates, and therefore you need to be careful in handling this matrix element here. What you can do is recognize that the Hamiltonian is the sum of the kinetic energy operator and the potential energy operator, and insert that form, and then let V operate on the right and P operate on the left. Okay, all right, and then use the eigenvalue equations, because position eigenstates are eigenstates of the position of the potential energy operator, and momentum eigenstates are eigenstates of the kinetic energy operator, right? And then you get the eigenvalues which are not the operators, right? And now that you have this eigenvalue e to the minus I e t over h cross, okay, you can move this outside the matrix element. Okay, so let us do it in the next step here. So e to the minus I e t e delta t over h cross is taken out. All right, so now let us analyze this further. You have got the momentum representation, okay, so this is e to the I p x, and then you have got a complex conjugate which will come with a minus sign, so it is I p over h cross x prime minus x. Fair enough? Now this is a typical segment in the elements which we were considering when we talked about alternative paths. So you have many infinite paths, right? And each segment here, for example, this is the path between x n minus 1 and x prime, which is the last step, right? This here you have the first step, and in between you have these intermediate steps, but each of these is a typical element like this, which will be expressed like an integral. So you have got the integrations over positions coming from here and integrations over momentum coming from here, because each of these element is a momentum integration. So we will write this as integration over position as well as integration over momentum. If you are now considering all possible paths, okay, there are infinite of them, so you can break the time interval into n parts, let n tend to infinity, so that the time interval itself becomes infinitesimally small, delta t tending to 0. You take all possible paths that you would like to consider, and each element being a momentum integral, now you have a set of position integrals and momentum integrals. So write it carefully, very easy to make a careless mistake. I may have made one, check it out, and if you find an error, please let me know. Okay. What are the integrals that you have to evaluate? Look at the integrand. You see that you have got a sum over j going from 1 to n, because each of these is an integral of this type, and you are multiplying these throughout, okay, and they are coming in the exponents, so they will get summed over. So you have a sum over j going from 1 through n, I over h cross comes out as a common, and then you have got this p x prime minus x over h cross is here, right, and then you have e I e delta t, which is here, right. So you have delta t over here, but you did not have it here, so you compensate for it by having it here. Okay, got it? We are all together? And these integrals can be evaluated. This is the integral in the momentum space. This integration can be carried out. These are Gaussian integrals, and I will do a little bit of digression and tell you how these integrals are evaluated. So this is the kind of integration that you have to carry out. Okay. Now in this, here you can pull out this term having the potential, because this is integration over momentum and there is nothing in momentum over here. So you pull it out, and then what you are left with is a typical Gaussian integral. Okay, so this is what you get for a typical matrix element, and you can see that the integrand over here has got this form e to the minus a times p square. Here is the p square and the rest of it is a. Okay, and then you have another term which is e to the power bp. Here is the p and the rest of it is b. Okay, the rest of it is I over h cross xj minus 1. So this is the b, right? And you will have this type of a coefficient for all values of j, because you are summing over j. Okay, so you need to evaluate integrals of this kind. As to what is the integral j, which depends on the parameters a and b. It is a integration over x, which is a dummy variable. You can call it x, you can call it y, y1, y2, whatever. It's a dummy label which is going to get integrated out. And when you are having so many of them, you can call one as y1, the other as y2, the other as y3, and so on. They all get integrated out, and that's what we are going to do. And each is going to have this form which I have written in the lower right corner as j, which is integral minus infinity to plus infinity x. This is some arbitrary variable. This is not the position coordinate. Okay, it is only the form of the integral that I am talking about. All right, the actual integrals are in the momentum space. So it's not that I am saying that okay, we have to evaluate integrals in the momentum in the coordinate space, but this is just a mathematical form that you have got an integration variable which can be x or y or p or y1 or y2 or whatever, where the integrand is e to the power minus ax square plus bx. That is the general form of the integral. So if we know how to evaluate this integral, we can plug the answer over here and move forward, right? So first I will discuss how an integral, the Gaussian integral itself, is done. I am sure that you might have done it in your previous courses, but it is a good idea to spend a few minutes and quickly recapitulate this. So you want to evaluate this integral, which is the integral of a Gaussian function, and the easiest way of doing it is to determine the square of this and then take the square root of the answer. Okay, that's a quick way of doing it. So this is your integral I, you take the square of it. X is a dummy label, so you can write it as, you can use x in one of the i's and in the other I you use y, and then you have an integral over x and over y, and the integrand is in terms of x square plus y square, because you have a rho square kind of thing coming there, right? And you can write it in polar coordinates. So x plus iy is rho e to the I phi. These are the plane polar coordinates that you are familiar with, and then carry out the integration not over x and y but over rho phi. Okay, so I square is this integral, and you need an integration over phi, which is very straightforward. You get 2 pi out of it, and then you have to evaluate rho e to the minus I rho square, and you can now transfer the variable. You can put s equal to minus a rho square. Okay, these are simple substitutions that gives you rho d rho equal to minus ds over 2a, and now you have the integral done very easily, because the integration over s is nothing but the integration of an exponential function. Okay, take care of the 1 over 2a and you get e to the power 0, which is 1, right, and you get I square, which is the square of the integral that you were interested in. So, the integral in which you were interested in would be the square root of this answer. Okay? So, this is the integral of the Gaussian function, but of course, we were interested not just in this, but in j. So, I would be just a part which will help us get the answer for the integral j, which is really what we are interested in. So, let us analyze this and remember that A was that remaining part which was minus I delta t over twice m h cross. You remember these terms? Okay. And we know what B is. So, it is with reference to this ax square minus bx that the integral j is to be determined. And if you do a little bit of manipulation of these terms using elementary algebra, you can factor out e to the b square over 4a, and what you are left inside is an integral which is just like a Gaussian integral, which you already know how to answer. Okay? So, knowing how to get the integration I, you know how to get the integral for j, and this is all you need. So, these are the Gaussian integrals which come in this expression here. Got it? Right? Good. So, now you plug in this Gaussian integral. So, you have this term which, remember, we had dragged out the term containing the potential energy. So, let us not forget it, it is sitting over there, right. And then you have this e to the b square over 4a, which is here, e to the b square, but b is this over 4 times a, but a is this I delta t over twice m h cross, right. And if you simplify this, root over pi a, you have square root of pi, and what is a? A is this I delta t over 2m h cross, which comes here. So, now you can simplify this further by multiplying the terms over here by this and get this square root, this, it is 1 over m here, so it ends up as square root of m in the numerator, right. So, it is just straightforward manipulation of this term. So, there is no big mathematics or big trick involved over here. And you have similar expressions for each of these infinite amplitudes, and you will have to multiply this by a similar term for the next step, by a similar term for the third step, by a similar term to the next step, and you multiply all of these. As you multiply all of these, the exponents of e will add up. Okay? And they are all contributing the same amplitude, but the difference is only in the phase. Okay? And what is coming in the exponent over here, you have got the potential energy over here minus V, which is goes into the Lagrangian, right. And what is this? You have half m, this is the delta x by delta t, which is the velocity. So, you have got half mv square, so this is nothing but the Lagrangian, right. This is nothing but the Lagrangian, this is just the Lagrangian t minus v. And you may have similar terms in all the each single element, but now you have to sum over j equal to 1 to n, and then let n go to infinity, let the time intervals shrink, become infinitesimally small. So you have got this I over h cross, okay. Delta t must come under the integrand, and you are essentially integrating the Lagrangian from time t0 to t prime. And what is that? That is action. That is how action is defined in classical mechanics, right? So you see how the principle of variation is showing its face over here. So this is the action, okay. You see the kinetic energy term and the potential energy term. From the difference you get the Lagrangian, and when you write all of these terms together, you can write it in a compact form, because the integration over time is that of the Lagrangian, and you have a rather revealing relationship which you have written at the bottom of the slide. Do you see how we have obtained this expression? No, if you have any doubt you can ask me, but I think it takes time to write these equations on a board, but if you focus on the concept and the discussion, recognize the terms because they are terms that you have used earlier, you should be able to appreciate the mathematical analysis very easily, even if we go through it so fast. Are we comfortable with this? Good. So we develop a compact notation to write what is in this blue box, okay, because you have infinite terms over there, you can indicate them by writing at least 3 or 4 terms, okay, but you can do so by developing some other equivalent notation, which is what is written here, that you write integration from x0 to x prime, and then you are having the integration elements dx1, dx2, dx3 and so on. All of them you write with a capital D and put x of t in the parentheses, and this is the notation that you develop so that you can write it in a more compact form, okay. There is no new mathematics, and now the same result is written in a compact form which looks like it has the same action as was used in classical mechanics. It is the difference between kinetic energy and potential energy. T minus V is what comes in explicitly. So this is the probability amplitude, and now you have got these phases. Some of these phases will be added, and if you write rho e to the I phi as a vector in a complex plane, okay, so you have got a complex number, you write the real part and the imaginary part orthogonal to that, okay, so real part on the x axis and imaginary part on the this, and the complex number x plus iy you write as rho e to the I phi as a vector in this complex plane, and you are adding these vectors, and these vectors you can add in phase because you are segmenting the time interval into n number of short intervals and then let that n go to infinity. But these n steps, you are adding n vectors, and they may be added in phase or out of phase. If they get added out of phase, you may even get a 0, or else you may get some other amplitude in which it is all added together, okay. And classical mechanics results when action is an extremum when action is much larger than the Planck's constant. So that is when things get added up. Okay, that is the reason that classical mechanics works. Okay, so in some sense Newton's laws work. Part of the explanation comes from the fact that they are consistent with the Lagrange-Hamilton formulation, and the Lagrange-Hamilton formulation works because it is an approximation to quantum mechanics. And what is quantum mechanics? We just described the path integral approach to quantum mechanics. Okay, so we have this, we can get this probability amplitude from conventional quantum mechanics by using the time evolution operator. But then we are going to focus on the right hand side of this equation. And in the right hand side of the equation, we are carrying out this sum over all possible alternative paths. Okay? So there are these three approaches to quantum mechanics, and there is fascinating literature, and I have been able to familiarize myself with just a small part of it. The literature is really very vast, but some of you will go beyond. So here are some references to start with, but then what is important is for us to recognize that the Feynman path integral approach is equivalent to the conventional quantum mechanics. We must convince ourselves that it is equivalent. We have seen what this approach is. You have to sum over all the histories. So how do we convince ourselves that it is the same? Basically, we are going to show, we are going to take the example of a free particle. Okay, and this is the interesting part on which I commented a little bit earlier as well, that between the scatterers, the Feynman particle goes in straight paths, just like a free particle. So it goes in straight path. So this is the straight path trajectory which is of importance. And if we can show that for this part it is equivalent to conventional quantum mechanics, then we can sort of integrate over the whole and say that okay, the Feynman path integral is equivalent to conventional quantum mechanics. So for a free particle, we are going to take the case of free particle. So we set up the Hamiltonian for a free particle. We know how to solve this problem in conventional quantum mechanics, and we will solve it using the Feynman path integral approach, and we will find that the answer you get from conventional quantum mechanics is exactly the same as you get from Feynman path integral approach. Now that will be very inspiring, because showing it for a free particle is not terribly restrictive, because the Feynman particles do go along straight lines between the quantum scatterers. Okay, so it goes from here straight to another scatterer, and then if it does not meet anything else, it can go to Mars, and then it gets scattered over there, and from there it does not meet anything else. So it is not taking curved paths in between. Okay, although sometimes when we draw these diagrams sloppily, they may look to be curved. All right, I don't even know how to draw a straight line on the blackboard. Okay, it ends up getting some wiggles. All right, but the Feynman particle doesn't go along any of these wiggles. It goes along a exact straight strict path from scatterer 1 to scatterer 2. It's a very strong condition. And for these straight paths during which it goes, it travels like a free particle would, right? And this Feynman particle could be an electron, it could be a photon, okay, or anything else. For the Feynman particle, the Feynman path integral approach tells you that this probability amplitude is given by this integral, in which we have used this shorthand notation here for the integration, right. In conventional quantum mechanics, we know that this is given by the time evolution operator, which is made up of this Hamiltonian. So, we will consider the Hamiltonian in a particular case, which is the Hamiltonian for a free particle, which is not interacting with anything else. We will evaluate this using Feynman formula and using the conventional formula, and in both we will get exactly the same result, which is at the bottom of the screen. Okay. So, this is what we are going to do in the next class. I will stop here for this class, because these are unless some of you have read this earlier from other sources or learnt about it from some other sources, this may be new idea. So, I will like this idea to sink in, and then we pick up the discussion from here in the next class. If there is any question, we can discuss it now. There is no complicated mathematics, there is only the Gaussian integral. I worked out how this Gaussian integral is done. So, when you come for the next class, make sure that you are very familiar with how the Gaussian integrals is done, because what we are going to discuss in the next class is again the Gaussian integrals, but we will get nested Gaussian integrals, a Gaussian within a Gaussian within a Gaussian within a Gaussian, because of these number of elements. So, the image of the Gaussian integral, what is A, what is B, and how do you get B square, and what is, you have to plug in the correct thing. So, it is very simple, but it has to be done swiftly, so that you can see the solution. Okay? So, spend some time working on it, and then we will pick up the discussion from this point in the next class. Okay, thank you.